Hello, good morning. In this video, we are going to footing, design footing, which will be rectangular, and plus the size of column over it is 230 by 330 mm. Okay, the given data will be the example is the value of P means the actual load over the column, that is 800 kilonewton, plus L means the floor to floor height is 3.2 meter, and plus FCK means the characteristic strength is 20 Newton per mm square, and the yield stress that is 500 Newton per mm square. Okay, this is the given data. With the help of this given data, we have to design footing. Okay, we have to design a footing with its steel, and also with the thickness means for the depth of footing is also very much important. Okay, now as the size of the column is 230 by 330 mm, so means it is not a square column, so for that purpose we will also keep the ratio similar to the ratio of the column for the footing. Okay, so let's start. Firstly, we will find out the area of footing. Okay, for the area of footing there are some minor solutions we have to make. First, factored load on footing. Okay, means the value of Pu is equal to 1.1 into load on column. Okay, now what is this? The 1.1 is the 10% of the load on the column, and the load of the column, okay, now it is 1200 is equal to 132 Newton. Okay, this is the factored load on the footing. Now let's find the area of footing, that will be AF is equal to working load on footing. Okay, working load on footing divided by SBC means the safe bearing capacity of the soil, and that will give, that is 132. So see, the working load is given, we have the factored load means divide this value with 1.5 divided by SBC. Now the value of SBC is 200 Newton per 200 kilonewton per meter square. Now with the help of this we will get the area of footing, that is 4.4 meter square. Okay, as the column is in the is not the square in nature, so same ratio will be for the footing. So the size of footing in proportional of column size. Okay, now see, the column size is 230 mm and 330 mm. This is the ratio, means the D by B ratio is equal to 330 divided by 230 is equal to 1.435. Okay, L by B, L by B, and L by B ratio means if we have to find the value of L, the L is equal to 1.435 times of B. Okay, same, but we have the overall area of the footing, that is 4.4. Okay, put the value, means area is equal to L into B Now the value of L is 1.435 B into B, and the area is 4.4 meter. Then the value of B will be 1.751. So we will make it a round figure, that is 1.8 meter. Okay, then for L is equal to 1435 into 1.8, which is equal to 2.58. Cover that value with 2.6 meter. Okay, so we will provide the footing size of about value of B and value of L, that is 2.6 meter by 1.8 meter. Here we get the value of footing. So next one, upward soil pressure. Upward soil pressure. See, the footing is transmitting the load of the column. Okay, load on the column which will go on the footing, and the footing will transmit that same load on the soil. So we have to just recognize whether the soil is feasible to take this kind of this weight. Okay, now for that, the P is upward soil pressure, that is P is equal to factored load on column divided by size of footing. Okay, now the factored load on the column is 1320 divided by 2.6 into 1.8 is equal to 282 kilonewton per meter square. Okay, here we get the upward soil pressure. Now one more thing is left, that is the permissible shear stress. Permissible shear stress, and that is tau V is less than equal to Ks into tau C. Now the Ks is equal to 0.5 plus beta C. Now the beta C is the ratio of short side of column divided by longer side of column. Now that is 230 divided by 330. Now we will get the value of 0.697. okay, that is beta C. Now put that value into Ks. Ks is equal to 0.5 plus 0.695, and here we get the value, that is 1.196, which is way greater than 1. So as per formula it is not possible to take the value of Ks is equal to 1. Okay, now the left is the shear stress in concrete, means the value of tau C. Okay, now the value of tau C is equal to 0.25 in root FCK. Okay, now 0.25 in root FCK is equal to, FCK's value is 20 Newton per mm square. Here we get 1.118 Newton per mm square. Now we will convert this value into kilonewton per meter square. Simply multiply this value with the 10 raised to 3, 18 kilonewton per meter square. Okay, and the value of tau P is equal to Ks into tau C, which is equal to 118 kilonewton per meter. Okay, after that, now we are ready for finding the depth of the footing. Firstly, we will start with the one-way shear. One-way shear. In the one-way shear, first we will draw a diagram. Okay, this is 230, this is 330, and 0.23, and this is 0.33. After that, a value of B and value of L. See, the value of B is 1.8 and the value of L is 2.6. of B is 1.8 and the value of L is 2.6. This is in meter. Now the thing is, for the one-way shear, the shear force will act at the D distance from the face of the column. Okay, D distance from the face of the column. Here the shear force will act. Okay, is the single at a time. The calculation of the single strip, which is looking wise, it looks like a wide beam. Now the shear force acting on the shaded area now means Vu is equal to uplift pressure, means the upward soil pressure, into shaded area. Okay, now the thing is, the shaded area, how you will recognize this distance? That is very much easy. B minus small b divided by 2 minus d, means the d distance from the face of the column. Put the value p into, in bracket, capital B minus small b divided by 2 minus d in bracket into L. Okay, that is equal to 282 into 1.8 minus 0.23 divided by 2 in bracket d distance into L is 2.6. Here we get the equation of 733.2 in bracket 0.785 minus of d, and this is our equation. Okay, after that the concrete will offer the resistance, so the shear resisted by concrete, that is Pux. Okay, now in terms of rectangular footing, with the shear resisted by the concrete, we will find this in X and in Y. Now here, that is tau C, means the shear resisted by the concrete, B into D. Okay, now the B distance will be alternative distance. With respect to x-axis, whenever you are calculating, you have to choose that is in the vertical portion. Means when you are calculating for x and this distance is 1.8, means the value of p, then you have to select the value of b, that is opposite side, that is 2.6, means the value of b in this case will be 2.6. Tau c 118 into 2.6 d, and the VUY tau c BD 118 into, this time with respect to y, that will be 1.8 into d. After comparing this equation, we will get the value of d, that will be 286 mm. Okay, make a bracket and name it as answer E. Now after that, next one, the two-way shear. Two-way shear. The two-way shear is also known as a punching shear. Okay, now the punching shear is always acting at the d by 2 distance from the face of column. Okay, for example, I am again drawing the same figure. Okay, but for the two-way shear, the simply difference will be that the shear force will be act on this shaded area. Okay, and this distance will be d by 2, and this one will also be d by 2. Okay, now here how the calculations will be. Firstly, the shear force acting on shaded area. Okay, So C means VU is equal to force into area. Okay, now the force is upward cell pressure 282 into area is equal to L into B, right? But the C, the shaded area means the total area minus this distance. Okay, this area. Now that is 282 into L into B means overall area minus L plus D in bracket B plus D. Okay, so the equation will become 282 into in bracket 4.68 minus 0.0759 plus 0.56 D plus D square. Okay, this will be equation number 4. Okay, then the shear resisted by the concrete, shear force resisted by concrete. Now the VU is equal to tau C BD. The formula will be same, but as the figure is changing, as per that you have to consider. Now in the first case the B was the alternative in terms of one-way shear. Okay, but in two-way shear the B will be perimeter. Okay, means the line which is acting at the d by 2 distance, this line. Okay, you have to take the perimeter of this. Okay, now then what it will be, 2 times of 0.23 plus D and plus 2 times of 0.33 plus D. Okay, now it will become 1.12 plus 4 times of D. This is the value of B. So it is equal to 118 into in bracket 1.12 plus 4 times of D into D. This will be equation number 5. Now compare equation 4 and 5 and there you will get the value of D, and here the D is 392 mm. Okay, up to here the one way and two way is complete. Now see, this is the answer of B. Okay, then next the bending moment. For the bending moment, we all know the formula of bending moment is WL square upon 8. Okay, now the thing is, for example, you have the footing and column over it. Now this distance will be xx, right? Now bending moment with respect to x and bending moment with respect to y you have to take out. Now okay, see the bending moment, firstly mu with respect to x, that is P, okay, upward solid pressure into capital B minus B divided by 8 square, and that will give the value of 86.89 kilo Newton meter. Okay, this is the moment with respect to x, and the moment with respect to y, that is upward solid pressure into L minus B divided by 8 divided by raised to 2, that will give the value 181.64 kilonewton meter. Always choose the greater value, okay, because the maximum will be the bending moment. As per that you are going to take the depth, okay, of footing. Then we will compare that mu limit is equal to md, and that is for as per the grade, that will be 0.133 into 20 into 1000. Value of B will be 1000 with respect to D square is equal to, now the value of MD was 181.64 into 10 raised to 6. Here we will get the value of D, and that is 261.3 mm. Okay, and this is the C. Okay, after evaluating the maximum, the most highest value between A, B and C, we will evaluate as the value of depth of footing. Okay, now the D is equal to 392 mm. That is the effective depth. Okay, means from the top to the reinforcement, this distance. Now we will take D dash, means cover, and bar diameter as the 20. So the overall depth is equal to effective depth plus D dash plus 5 by 2, and that is 392 plus 50. Cover is our 50 plus 20 divided by 2, and here we will get the value of 452 mm. So say the overall depth, means value of D is equal to 460 mm. Now again we will cover up the value with the effective depth, and the D is equal to the overall depth minus 5 by 2 minus D dash, and it will be 400 mm. Okay, this is the depth of footing. Okay, after that we will find the reinforcement detailing. Reinforcement in X direction and in Y direction. Okay, now so the area of steel, means AST is equal to 0.5 FCK divided by Fy in bracket 1 minus in root 1 minus 4.6 MD. See the maximum bending moment 181. Here we will take the value of bending moment with respect to X and with respect to Y. Okay, not the greater value as per the direction mentioned. MD is equal to that value, and the FCK into BD square in bracket B into D. Okay, after that we will put the value 0.5 into 20 into Fy is 500 in bracket 1 minus in root 1 minus 4.6 into 86.89 into 10 raised to 6 whole value divided by FCK 20 into, here the value of B will be 1000, because while designing the footing always you consider the footing as the 1 meter square. So convert that value into mm, that is 1000 into value of D. The value of D is 400, which we come forward, and the 1000 into 400 again overall multiply. This the value in X direction, we will get the area of AST, that is 516.27 mm square. Now with respect to X direction, the spacing will be for the 10 mm reinforcement in X direction, S in X direction is equal to 1000, means the value of B into area of diameter of bar into AST in X direction, that is 1000 into pi by 4 into 10 square divided by the value of AST which we come through, that is 516.27, and the value will be 152.13 mm. So provide 10 mm diameter bar at 150 mm center to center. Here the design of footing with respect to X direction is completed. As our footing is rectangular, so the in Y direction, AST in Y direction is equal to 0.5. The formula for AST will be same, only the directions will be different because the bending moment changes with respect to direction. 5001 minus in root 1 minus 4.6 into 181.64 into 10 raised to 6 divided by FCK means 20 into 1000 because of the value of B, and that is 400 full bracket into 1000 into 400. Here we will get the value of AST in y direction, that is 1123.3 mm square. Okay, for this also the spacing for 20 mm diameter bar in y direction, that is the formula will be same as y is equal to 1000 diameter of bar divided by AST in y direction. Here after this calculation you will get the value of spacing, that is 270 mm center to center. So provide 20 mm diameter bar in y direction at 270 mm center to center. Okay, here the complete calculation related to footing is covered. At the last, one of the most important thing where the marks are gone, that is summary. Whatever calculations you are made up to now, you have to write in the summary, and that is, for example, we have done the column design, means the size of the column that we evaluated, that is 230 by 330 mm. Then the reinforcement in column, that is 6 bars of 22 mm longitudinal bar. Then the lateral ties of 8 mm at 230 mm by center to center, and the footing size, that will be 1.8 into 2.6 meter. Then the reinforcement along 1.8 meter, there was, see the diameter of bar at 150 mm center to center. Then the reinforcement along 2.6 meter longer span, that was 20 mm diameter bar at 270 mm center to center. This was the overall scenario, the summary, the detailed calculations, and after that you have to draw the figure, which is firstly the plan, and the second one, that is section. In plan completely you have to show what type of calculations you made. This is our footing, here the column is located. Then you have to show the reinforcement. Okay, in x direction, also in the y direction, you have to properly name it. Now the in longer span, see these rods means 20 mm diameter at 270 mm center to center. Then this, the shorter span 10 mm diameter at 150 mm center to center. Then the grade means M20 and FE 500. Okay, means the M20 FCK and FY, that is FE 500. Then the value of L, which is 2.6 meter. So this is our plan, and now the section. Now for the section, just take a reference of the column and draw like this. Okay, B is equal to 1.8, right? So the reinforcement detailing. Okay, up to here it is all correct. Now the lateral ties. See, the lateral ties are about 8 mm diameter at 230 center to center, 20 mm 20 mm diameter at 270 mm center to center, and here for the shortest span, that is 10 mm diameter at 150 mm center to center. This is the overall calculation of footing. The total pages required to solve this particular kind of example, it is near about 6 to 7 pages. At least solve this example for 4 to 5 times, so that we will able to solve the design of footing. Thank you.